Hi, and welcome to our supplemental video on scalable supervised learning with the extreme value kernel machine for ICML 2015. Core of our paper comes down to a theorem that shows what we call the EVKM kernel theorem, that shows that given a non-degenerate kernel exists and you have enough samples and a well-defined margin, then you can show that the distribution of distances from that margin converge to a viable, and that the probability of a point is within the margin associated with the given point is given by the reverse viable CDF. Here we see that as e to the minus the distance between the points divided by lambda I, all raised to the power kappa I. That's our reverse viable CDF. And that kernel provides our way of trying to estimate data. This gives a nice theoretical foundation. This video is going to briefly show you, give you some intuition about these, which is a little harder to get across in the paper. So we're going to be able to show you some examples. In this example, we have three negative classes, the shapes, and a positive classes shown with four sample points A, B, C, and D. And here we're sort of showing you the probability of something be associated with a point D. It's given by this surface up here. The projections down here show you rings of different confidence levels. And that's true for each of these. You can see the wide variations of shapes that are going to be possible. So here we have a very rounded shape, but these are almost cylindrical. The way this data will be fit is described in the paper. We're not going to go into in the video. But as the data is sparser, you tend to get these smoother shapes. As the data becomes denser, you'll get these straighter shapes. And it's also a function of the tail size. The video in a second will go off and we'll show you the tail sizes as we vary that, so you can get a feeling for what happens. We'll also show you it from a top-down point of view, where here we're just seeing the density. Red means probability is very close to 1. Yellow is in the middle. Green and blue, if you see any blue, will be at the very close to 0. And here we can sort of see the data density issue again. This cylinder has very sparse data and with one almost outlier. So the probabilities here are very slowly decaying compared to C, which gets data from all of these classes, where A is driven mostly by what's close to it. And we'll see that in the video. So here you can see as the tail size increases, the functions tend to spread out because the definition of the margin moves deeper into the data with a larger tail. And they also tend to smooth out as the tail includes data of varying distances away. As we go through this one more time, you can look at the probabilities. Remember, the way these will be used in a multi-class setting is we'll choose the highest probability from any class, and then threshold to make sure we don't label too much open space. As you look at this, the yellow area is probabilities less than 0.5. So when you think about where the margin is, sort of look at the line between red and yellow. That's around the 0.5 probability. You can see these can support soft margins as it includes the outlier point in D within the class. So now that you've seen what the kernels are, the paper goes on to look at this in terms of scalable machine learning and using those kernels in a kernel machine. By scalable, we mean large number of classes and examples. So the first scalable data set we look at in this paper is the Alloy data set, which has 1,000 classes and over 100,000 samples. To allow comparison to the prior literature, we also include Letter, MNIST, and USPS, which have much smaller number of classes and smaller numbers of samples as well. To see the kind of performance you'll see in the paper, on the Alloy data set, the one we're looking at scalability, we have the highest accuracy of any of the algorithms tested, beating the best state-of-the-art, an algorithm by Anderson Roach et al. That has about 93% accuracy. With this algorithm out of the box, no tuning or anything, you get 94% accuracy. You'll also see the algorithm is more than 5 times faster than a standard 1 versus rest SVM during test time, and a little bit slower during training time, with a lot less extreme vectors compared to the number of support vectors. We're also going to compare with a WSVM, an open set recognition algorithm that was published in 2014. You can see here its accuracy is considerably lower, and its recognition at test time is more than twice as fast. We don't actually have the testing times for the state-of-the-art algorithm, but its accuracy was around 93%. On the classic data sets of Letter, MNIST, and USPS, where you have a much smaller number of classes, and again, all of this is closed set testing following the standard protocols. Our EVKM algorithm, where we used all the data instead of the hard data, gets 95%. But just out of the box, the faster algorithm for training, you'll see the training time is considerably faster for the EVKM, not using all the data, gets 94.9, and statistically these are within the error bounds of each other. Test time orders of magnitude faster than the WSVM, and 5 to 6 times faster than a classic 1 versus rest SVM, which out of the box does not do extremely well on letter. On MNIST out of the box, everybody does better in terms of accuracy. The EVKM is still the more accurate one. EVKMA is not shown because it took too long to compute. We give up after 500 hours of CPU time. And again, the EVKM is considerably faster at test time than the other algorithms. On USPS, which is a very small data set, test times are faster. Again, the EVKM algorithm is significantly faster than the others. Accuracy for all of these are in the high 90s, 96.6% for us, 96.1% for standard SVM. So all of these we would just say are really comparable in terms of where they're going to end up. They're all within standard deviations of each other. So the more important part of the paper then is looking at how this works on an open set testing, where we might know all the parameters or all the classes. So if we train on all 1,000 classes in Alloy and test on all 1,000, we're over here. But what happens if we train and we don't get to have all the classes during training, but in testing some other classes might show up? So if we're out here at 50%, it means we trained on 500 classes, but during testing all 1,000 classes show up, and we have to correctly reject the unknown classes as unknown. This impacts the performance of the EVKM, but not near as much as it impacts the performance of 1 versus rest SVM or the WSVM or another open set algorithm that's been recently introduced called the PySVM. And as you get down to only 10%, so you only saw 100 classes, but during testing all 1,000 show up and you have to reject as unknown lots of them, the F measure for the EVKM is still close to 50%, where the other algorithms are down in the 30s or in the teens. So EVKM is faster, very good with its default parameters, and for open set testing is the best performing algorithm on this Alloy dataset, and for both closed and open set testing. Look forward to seeing you at ICML.